Hi everyone. I am Egor, and I work in YTsaurus in the scheduler team. Today, I will tell you how scheduler works, how to run computations in a YTsaurus cluster, and how resources are allocated across such computations. Let me briefly outline my presentation. First, I will talk a bit about the compute subsystem of YTsaurus, and then I will show some basic examples launching operations in it. In our terms, operations are computations performed by users. I am going to dedicate the major part of my presentation to allocating resources across such operations. Finally, I will talk about some advanced scheduler features that enable configuring operations and resource allocation in a more flexible way. I want to make my presentation as hands-on as possible, so let's switch to the demo mode right away. First, let's talk about the cluster. We have a small demo cluster with 24 cores and 60 GB of RAM. These are the computing resources the user operations may use. I'd like to highlight some terms straight away. By operation, I mean computations performed by users. A user will typically take certain input tables, convert them based on a simple principle, and give them back, e.g., write output tables. When an operation is launched on production cluster nodes, it is split into multiple jobs. A job is an atomic part of computations that is run in a container on a node and processes a piece of input data. Why am I specifically highlighting this? Because many other similar systems, such as Hadoop Yarn, use job and task for that, respectively. In our system, they are called operation, which is a single large computation, and job, which is a part of an operation. So, a scheduler is a core component of the YTsaurus compute subsystem. Look, we've got one here. The scheduler has three purposes. First, it accepts user requests to run operations. Second, it works with nodes, exec nodes, to be more precise. Nodes send regular heartbeats to the scheduler, telling it how much of free resources they have. The scheduler replies with which jobs the nodes need to run. The scheduler takes jobs from operation controllers. These are entities that reside on controller agents, which are separate cluster components. An operation controller understands how to split input data into jobs, which properties to set when launching a container on a node for each job, etc. Basically, it manages the way the operation is being run, while the scheduler takes jobs from the controller, as if it were sort of black box recorder, and runs those jobs on nodes. Last but not least, the scheduler manages resource allocation. Typically, you won't have enough resources in a cluster to serve all jobs. This means the scheduler has to decide how much resource each operation deserves and run the jobs accordingly. Let's move to our first example and launch our first operation. I've got a Jupyter notebook here. You can access it through the link in the description. Let's run a very basic operation. In my case, it is a map operation that just gets some input data, takes a sleep for 60 seconds, and delivers what it got as output. Basically, what is of interest here is how it looks in the YTsaurus UI. Here is the operations page where you can find the operations you need through filtering. By default, the operation list is filtered by user and status, running. Now let's see what we have for an individual operation. First, we've got some metadata that tells us how it was launched. Here is some info on how it ran, some runtime properties, etc. There is also a job list, which is of more interest to us. Just as on the operations page, there are some filters for jobs. For each individual job, you can view which node it was started on, its start time, finish time, and other info. Meanwhile, our operation is over. Let's see the Statistics tab. Basically, statistics are certain numbers calculated for a job on a node. For finished jobs, all stats are sent to the relevant operation. This is not that important in our case, though, as we only have one job. However, if there are many jobs, it may be handy to view average and maximum values, etc. To learn more about statistics, what they can be and what they mean, we can view our documentation. For example, let's have a look at max_memory. It says our job consumed 580 KB at its peak. Seems fair, as it does not really need much memory. Finally, the Specification tab shows the operation specification, or spec, for short. This is a JSON-based text that tells you what the operation needs to launch, and how. In particular, here is the command I provided. Just a bash command run inside a container. In the mapper section. Here is also the input table, the output table, and, basically, a lot more info that Python API provided for us. I mean, for me. This is called the provided specification, IDS, the one the scheduler got. If we go to the resulting specification, there will be many options you can use to manage the operation run properties. I won't be covering these options now, but for a few individual ones. I won't be talking about the operation types either. If you want to learn more about various ways of running your operations, I suggest you refer to our documentation. Meanwhile, I'm here to talk about resource allocation. So, let's move to our next example and start a few operations. Here and elsewhere, I will be using vanilla operations. These are basic operations where a user says they want a certain number of jobs, 3 in our case. Each job having a certain amount of resources, in our case 2 KBs, and run a certain command in a container. All my operations will now enter the sleep mode, so that I could show you how the resources are allocated across them. So, I started 6 operations, each wanting 6 KBs. Let's refresh the page to make sure they all started. In total, they want 36 KBs. While I previously mentioned our cluster only has 24. Let's go to the scheduling page to see how these 24 KBs got split across our operations. But first, let me clarify one thing. When it comes to resource allocation and resources in general, the scheduler thinks of resources as cluster shares, rather than of absolute numbers, such as one CPU. In our case, that means a share of the total number of KBs, 24. Each operation wants 6 KBs, which makes 1/4 of the cluster. Here we can really see that the demand is 0.25 for each operation, while in total, they want 1.5 clusters. Meanwhile, the usage, which means how many resources they actually consume, is 1/6. What does fair share mean? This is actually a key concept when it comes to how the scheduler works. Fair share is the amount of resources an operation is due in the scheduler's point of view. What does this actually mean? This means that the scheduler has a 2-stage algorithm. First, it scans the current situation in the cluster, checks which operations have been started, and determines the fair share. Based on a certain algorithm, it sort of determines the target resource allocation, and then tries to run jobs, so that the usage might be the same as such target allocation. In real life, when it comes to a production cluster, it won't be the same. Rather than that, there will be a continuous race for resources, as the situation is ever-changing. And the scheduler will have to always approximate the usage to the target fair share. However, the fair share is also changing as new operations start, some jobs finish, etc. Why did the scheduler, in our case, give equal amount of resources to each operation? That is, why did each operation get 1/6 of the cluster? This is because fair resource allocation is a core requirement to the scheduler. In our case, which is a simple one, fair means equal. How can one manage resource allocation? This is what I am going to cover in a major part of my presentation. The first option you have is weight. We can see each operation has it. In our case, the weight is equal for all operations, while generally the fair share allocates resources in proportion to weight. Let me show you how it works. Let's move to the next example, where I start 3 operations with the weight of 1, 2, and 3 respectively. Let's wait a bit and refresh the page. Here we go, 3 operations started, and the fair share is 3 to 2 to 1, just as the weight values go. We can't see the actual usage yet, but that's just because the page didn't get refreshed. Right, I refreshed the page, and we can see the scheduler started the jobs so that the actual consumption and the target one match. Great! With weight, you can tell the scheduler which operations and processes are more important than others. But this is just not enough. And here is where the computing pools come into play. A pool is an entity that manages quoting computing resources. Just like in the YTsaurus storage system, where every table belongs to a certain account. Every operation in the YTsaurus compute subsystem runs under a certain pool. In this case, all our operations run under the admin pool. If we delve into the tree of our structure. Yeah, I forgot to mention an important point. All pools are part of a hierarchy, which we call pool tree. It is this tree structure that determines how the fair share will be allocated across the operations. How does it work? Let me describe this briefly. The root of our tree has all available resources, that is, 100%. The scheduler looks at the first tier of the hierarchy and sees all children, that is, all pools that want resources. Then, it just allocates the resources in proportion to the relevant weight values. Then, each pool gets a slice of cake, and this goes on and on, top tier to bottom, until it gets to the lowest tier children. That is, to the lists that are actually operations. This way, each operation finally gets a certain amount of resources. Let's see how it works in our next example, where we start operations in 2 pools, A and B. Both are in the example subtree. Let's wait a bit until they run. For A, I initially set the weight to 3, so the resources got allocated as 3 to 1. That is, 75% and 25% of the cluster resources. The operations within these pools also got resources on the 3, 2, 1 basis. Basically, this is what I copied from the previous example. Now it's high time to talk about how the pools work and how the relevant tree structure is designed. Let's abort the operations. I'm also adding a small helper for further convenience. Great! So, let's talk about the pool structure. The A/B example is a good thing, but in real life, pools will most likely look as follows. First, the pool structure is hierarchic, same as a company structure, where you have various departments. Each department may have multiple teams, etc. So, pools, in a certain way, mimic a company structure. On the other hand, workflows also fall into various types. In this example, I created 2 pools for 2 teams, development and analytics. In development, there are another 2 pools for different load types, production and testing. Actually, the same is true for the analytics pool. Thus, we roughly mimic the pool structure in a production cluster. The next question is how to configure pools and manage this structure. What helps us here is that pools, just like many other cluster entities, are Cypress objects. As you may already know, Cypress is our unified fault-tolerant metadata tree. Now, to create a pool, let's move to our next example. Using the common create command, we create an object of the scheduler_pool type, give it a name. Specify the parent name, if required, and the pool tree name. You can also have multiple pool trees. This is what I'll cover at the end of my presentation. So, let's create a pool. Now we can see that the example pool now has. Let's refresh it. Now has the C pool. You can also create pools through the UI. Here in the top right corner, there is a lamp icon that says Create Pool. I'm now creating a pool, and it appears in the cluster. Since pools are Cypress objects, you configure them through Cypress as well, using the appropriate attributes. I will talk about it in detail a bit later. For now, let's remove our pools. We'll remove D in the same way it was created, through the UI, while the C pool, using the remove command. As for configuring pools, I said you can do it through Cypress. However, you can also do it through the UI. Here's the pencil icon. Let's click it to open the settings. You can edit them right from the UI. I will cover some of those settings a bit later. What you can also get with Cypress is managing access permissions to pools. The permissions are based on the common ACL tools that are the same for the entire cluster. To run an operation, you must have the use permission for the relevant pool. You get this permission is a regular way through the ACL tools. Well, now let's move to the next important topic. In my last example, I started an operation in the A and B pools by explicitly specifying a pool. However, I did not do that in the previous examples. By default, a pool gets the same name as the username under which the operation is started. This is why I first created the admin pool, and then all my operations ran under it, as I'm currently singed in as admin. But what is going to happen if there is no such pool with the same name as the username? Well, let's see. Before starting my presentation, I created a user named Other and issued a token for it. You can read more about it in the authentication section of our documentation. Now, let's start a similar vanilla operation in the sleep mode through CLI. Let's find it and clear the filter by user. Here we go, there's an operation. Run under the other user in the other pool. However, as you can see, this other pool is an ephemeral pool, as the ghost icon and the relevant tooltip say. Such pools do not exist in the Cypress. They are created in such situations when the relevant pool was not created manually. When the last operation in such an ephemeral pool finishes, it is automatically removed. Right. What is interesting about it is that this pool was created in the research pool, under the company hierarchy. Why is that so? Just because I configured the tree this way. Well, let's stop this operation. I will do it through the abort button on the operation page in the UI. So we can see. We'll soon see once we refresh the page. Here we go, we're in root again, as the pool disappeared. Now let's look at our tree configuration. The tree is under the sys/pool_trees/tree_name path. In our case, the tree name is default. We are particularly interested in the config attribute. Here, the default _parent_pool option tells us where the ephemeral pools will be created by default. To conclude this topic, I want to give you a tip. First, you may want to create pools for each type of workflows with meaningful names and in appropriate tiers of your hierarchy. Then, you should explicitly specify those pools in your operations. Sometimes, however, users either don't want or cannot explicitly specify a pool for one reason or another. This is why I suggest the following workflow. You can create users. By a user, I mean a YTsaurus object, and split the operations you run by users. This way, you will run processes under certain users. After creating pools for those users in the relevant tiers of your hierarchy. Actually, many processes running on our production clusters follow this workflow. All right, let's move to the next topic. It is good that we have a hierarchy to allocate the resources top-down and certain weight values that can tell the system that production is, say, 10 times more important than testing. However, in real life, most companies tend to work with the quota or guarantee concepts. Of course, there are similar options in YTsaurus. You can configure a guarantee for a pool. Let's configure one in this example. What can we generally say here? First, the guarantees are also hierarchic. This means that, to provide a pool with a guarantee, you need first to provide it to its parent, and then configure its part for the child pool in question. The total guarantee amount for all children must not exceed the parent's guarantee. To set up a guarantee, use the strong_guarantee_resources attribute. Here, we can see our pool received a guarantee. To see the absolute values for guarantees, we can go to the Details tab. There are also absolute values for usage, fair share, demand. And here's the guarantee. It is provided on the 420 basis, and, for development, it got broken down into production and testing. So, how does the algorithm we talked about before work when there are guarantees? I'll start some more operations, and while they are starting, I'll describe a new algorithm. Again, initially, we have 100% of the cluster resources. The scheduler aims to cater to the first hierarchy tier. But now, the child objects that have a guarantee are served first. If such a child wants an amount of resources that is less than the guarantee, the scheduler takes the required amount and fully serves it to the child. If the child wants more, the scheduler takes the amount equal to the guarantee and provides it to the child as fair share. Once the scheduler is done with such pools, there are still some resources left. These are the resources it will allocate based on the weight. This means a pool may get more resources than the guarantee allows, in proportion to the weight of such surplus resources. Then, this goes on, from top tier to bottom, so that the individual operations also get their fair share. Here, we can see how it happened. I configured resources. Well, let's get back to company. I assigned all resources, so there are no free resources left. Look, analytics got 1/6, which is guaranteed, although it wants more. This entire guaranteed share went to the chit pool. The same happened to development. For instance, testing wants 1/3 of the cluster, but it only got 1/6 because this was guaranteed. Meanwhile, production does not exceed its guarantee. What is much more interesting is what happens when the pools do not want as much resources as they are guaranteed to get. Let's abort some operations, namely, an operation from the chit pool and another one from the production pool. So, what happened? In simple terms, when the guaranteed resources from the chit pool freed up, they got allocated to other pools in the same tier. In our case, they were assigned to the buy pool. The same happened to the production pool. You see, it currently wants less than guaranteed, and the remainder, 1/6, went to the testing pool quite naturally. What do I actually want to highlight? Let's assume you somehow configured the pool hierarchy in your cluster, which mimics your company or department hierarchy. And each pool has a guarantee. Let's also assume there is a pool that does not consume as much resources as it is guaranteed. In this case, YTsaurus scheduler guarantees that these resources that are currently free will by all means get reallocated within your pool structure rather than be taken by some random users. This is how it works when your structure has any pools that want resources. Otherwise, those remainder resources will be assigned to a higher tier. This is what we sometimes call resource isolation. Apart from guarantees, which are the lower boundary for fair share, we also have limits. A limit is a fixed upper boundary. In this example, I assigned a limit through the resource_limits attribute to the testing pool and started an operation there. The limit is 5 CPU, while the operation wants 8. Now, we can see the limit in the UI, and the operation is really getting no more than 5 cus. Limits have a higher priority than guarantees. This means, if the limit were 3 cus and the guarantee 4 cus, both the operation and the pool would get no more than 3 cus. Let's clear it out. Let's move to the next important topic. Up to now, I referred to the resources either as a cluster share, which is an abstract value, or as CPU. An absolute value, such as 24 cus in a cluster. There are, of course, other resource types. Basically, YTsaurus supports 5 types of resources. Let's have a quick look at them. They are 3 primary resource types: CPU, RAM, and CU, and 2 secondary ones: network and user slots. Network does not mean real network bandwidth. This is just a dummy resource that does not allow you to run, for example, many network-intensive jobs on a single node. Sort of a limiting tool. Network-intensive jobs are, for instance, those that belong to the sort operations. User slot is also a dummy resource, but it is easier to understand. Every job needs exactly one user slot. How can one use it? Let's assume you want to launch an operation with 100 jobs. However, you want no more than 10 jobs to run concurrently. In this case, you can add resource_limits user_slots equals 10 to the operation settings, or to the relevant pool 1 tier above, and the operation will get no more than 10 concurrent jobs. However, for simplicity, let's say we only have 2 resource types, CPU and RAM. Well, CPU is also a primary resource type, but we don't have any CUs in our example here, so we'll be considering only 2. Basically, the scheduler takes both of them into account when assigning the fair share. How does it work? Let me start 2 operations. One will want 2 CUs and 1 GB of RAM. The other will want 1 CPU and 10 GB of RAM. Let's find them. Go to Company, Development, Testing. Yeah, right. Oh, sorry. I was too quick and aborted them. Well, never mind. How does the scheduler actually see various types of resources? Well, I already said there is fair share, usage, demand, and guarantee, and it looks as if it were a single value. To see whether this is true, let's look into the pool attributes. This is some in-depth data we get from the scheduler. Each of these values are basically 5 numbers, 1 per resources. We call these numbers vectors, and indeed, they are real 5-dimensional vectors. As we mentioned, the scheduler sees the amount of resources as a cluster share, and now it becomes crucial. This enables comparing the amount of resources of various types. For instance, we can see that the entire testing pool currently wants 19% of the cluster resources in terms of RAM, and 1/8 or 0.125 of CUS. So, the pool wants more RAM than CUS. When a pool or an operation wants more resources of a certain type than of other types, such resource type is called dominant. Basically, all this time, we could see the dominant resource type in the UI in a separate column. Here we can see that one operation wants more CUS, and the other wants more RAM. Thus, the value of the dominant resource, or dominant share, as we call it, is shown here in the UI, and is actually the most important value from the vector. In particular, you can see that the total usage value of these two operations is far from equal to the pool's usage. This is because they have different dominant resources, so their vectors summed up, and the pool's total binary share is less than the total of its children's dominant shares. So, why is it important that the YT scheduler supports resource vectors? Well, let's take a look at an alternative approach to resource allocation, the one we actually had for a long time as well. This is the approach when the resources are allocated simultaneously, based on a certain ratio. For instance, there is a global setting that says that every operation gets 4 GB or RAM per CPU. As I said, this is how it previously worked in YTsaurus. That is, for example, once we provided a guarantee for CUS, all resources, or fair sharing in terms of resource allocation, were provided in terms of CUS, or more precisely, in terms of the cluster share. Basically, the guarantee provided, say, 10 CUS, while the guarantee for RAM was calculated implicitly based on the current ratio within the cluster. Why is this inconvenient? First, it is clear that a single value is just not enough to cater to this variety, when operations of different types want different amount of resources and have different dominant resources. Second, let's use a simple example where you have an operation that wants more RAM than CUS, while you only have an explicit CPU guarantee. Such an operation will be limited by the implicit RAM guarantee. This way, to fully cater to this operation, that is, to enable it to start with all required resources, one would have to increase the CPU guarantee so that the RAM one also increases. This is not transparent, and besides, if your company pays for resources, you will have to additionally pay for that CPU guarantee you don't actually need. So, this is inconvenient. This is why, a few years ago, we completely reworked our algorithm, where the resources are just allocated top-down. Now this algorithm is more complex as we added some features, and the scheduler sees the resources as vectors of various resource types. One of the features we added, actually, the most important one, is vector guarantee. This is exactly what the name suggests. You can now assign guarantees. Let's move to our next example, based on various resource types. In this example, I am assigning a guarantee of 4 CUS and 16 GB of RAM to the CHIT pool. The scheduler's algorithm will be now considering that the hierarchic nature is still there. The total guarantee for children cannot exceed the parent's guarantee. This is why I'm assigning these 16 GBs at the top tier through the same strong_guarantee_resources attribute. Let's go to the CHIT pool. Here, we can see it still has the 4 CPU guarantee. When we move to the Memory tab, we'll see it now has the 16 GB guarantee, too. Great! Basically, this almost concludes our talk on resource allocation. We have pools within a hierarchic structure. We can assign guarantees, limits, and weight, and this is already quite a flexible tool that allows us to prioritize certain computation processes within a cluster. The last topic I'd like to mention is another part of the scheduler algorithm, the one that runs jobs. Particularly, we are interested in the preemption concept. Let's imagine the following situation happening in a cluster. An operation started. Let's find it first. So, here it is. It wants 20 cus, which means 20 jobs. There are no other operations that need resources, so it got its 20 jobs. Then, another operation followed. It also wants some resources, say 12 jobs or 12 cus. Both operations have the same weight values, which is why both have been assigned 50% of the available resources, on the fair share basis. However, we can see that the second operation only has 4 jobs started. This is because, at that particular point in time, only 4 cus were free to use. How does the scheduler solve such tasks? How does it align usage with the target fair share? Here is where preemption comes into play. First, this tool detects the operations that do not get enough resources they need over a certain time, which is customizable, and marks them as starving. Such starving operations are candidates for preemption. The question is, which jobs can be preemptible? At the same time, the preemption tool finds the operations that consume too much resources, lists their jobs by start time, and marks the jobs whose usage exceeds the fair share as preemptible. Let's look at the attributes. Here, we can see the preemptible _job_ count attribute. It shows us that 8 jobs out of 20 are preemptible. The scheduler can actually abort such preemptible jobs in order to free up resources for the starving operations. Why is it not doing this in our particular case? Well, just because I disabled this feature in the testing pool before showing this example to you. Let's now enable it to see how, by job, the resource allocation will be becoming fair. The preemption tool is somewhat slow because otherwise it may cause unwanted turbulence. So, now we can see the fair condition is achieved. Either operation got 50% of the resources. It is also a good idea to open the properties of the first operation, the one we wanted to preempt, and view the list of its jobs. As you can see, 12 jobs are running, while other 8 were aborted. When we go to the error page to see why a particular job was aborted, we'll see it was actually preempted. If we further expand this error, we'll find even more info, that is, which job was the reason for preemption, as well as some debug information. Great! The preemption tool will actually conclude the core part of my presentation about resource allocation. I am now moving to the final part, where I will talk about the scheduler's advanced features. The first one is FIFO pools. FIFO is a mode you can configure for a pool. This is an alternative to fair share, which is actually the default mode for pools. Do not confuse this fair share mode with the fair share term we mentioned before. As a pool mode, fair share means the resources in a pool are allocated based on the weight values, sort of equally. FIFO mode works in a slightly different way. First, it sorts all operations running in a pool. Then, it takes the entire portion of resources it got from the resource allocation algorithm and offers it to the first operation in the list. If the first operation is fully served, it moves to the second one, etc. As a result, some operations will be fully served, one will only get a fraction of the resources it needs, and some will just get zero fair share. How are the operations actually sorted? Well, this is also customizable. As the name, first in first out, suggests, they should be sorted by start time. However, in our system, by default, they are sorted by weight, descending, and only then by start time. Actually, these two values, weight and start time, are technical reasons why a FIFO pool can only have operations and cannot have nested pools. Let's see how a FIFO pool actually works. Here's our guinea pig, the testing pool, and I'll now set its mode to FIFO. So, let's go company, development, testing. Let's refresh the page. Here, it got the FIFO icon, and each operation now has a FIFO index, which is its number in the list. Now we can see that the demand for the first 4 operations is fully met. One more operation only got a part of resources, and another one, 0. If we start an operation with a larger weight, say 100, it will be taken to the top of the list and will be fully served, kicking the job of the last operation. The last but one, I mean. The next feature is what I briefly announced before, multiple pool trees. What is a pool tree? It is not only the pool structure through which the resources go. It is also a pool of resources. Namely, this means the nodes where you can run jobs and the operations within this tree. You can also break down cluster nodes into multiple pool trees. How does this happen? Every node has some tags assigned. These are either system tags, that is, assigned by the system, and user tags, the ones the users may assign. Meanwhile, every tree has the filter by tags option. A filter is a Boolean formula, and once a node meets this formula, it is automatically matched with the relevant tree. Each node may only match a single tree. When this is not the case, the scheduler fires an alert and the changes are not saved. In this example, I first filter exec nodes out of all cluster nodes. Then, I assign the custom underscore tag to the first node. Configure the no custom underscore tag formula for the default tree, and create a new tree with the custom underscore tag formula. Again, these are common Boolean formulas. They may look like tag underscore 1 and tag underscore 2, and then tag underscore 3, or tag underscore 4 in parentheses, etc. On the scheduling page, we can now see a new pool tree called Other. It has one node, which means 8 We can also see an alert. This is another type of alert that is also worth talking about. This alert appears when a tree, in our case, the default tree, does not have enough resources to meet the related guarantees. As you may remember, I provided as many as 24 cus, while now there are only 16 left. In this case, the scheduler, first, points this out by firing an alert and, second, gradually bites off a fraction of guarantee from all pools at the same time, so that there are enough resources for the new guarantee values. This is a sort of emergency tool. It will allow the system to continue working properly in such cases when, for example, some nodes are no longer available. You can also run operations in multiple trees at once. Here, I created the testing pool in a new tree and ran an operation in 2 trees at once. Let's find this operation and open its page. Right, we can see there are 2 trees for it. There are also 2 trees in the section with time properties. As you can see, all 24 jobs started, that is, on the nodes of both the first tree and the second one. Now that we are here, let me put it as a side note that the runtime properties, such as the pool and the operation wait, can be edited both through the UI, right as you can see here, and through the API, of course. Let's clear everything out and move to the next example. Let's talk about speculative jobs. Running a speculative job is a common tool used when, say, you have a multi-job operation, and there's a job that is running on a node with a slow disk. So, this job is very slow. The scheduler, if we tell it so, may understand something went wrong and try to run a speculative copy of such a job on another node. These 2 jobs will then sort of compete against each other. The first one to finish will win. Its output data will join the operation's output data, while the other job will be aborted. Let's look at the operation I just started. While I was talking, the second one started too. Let's have a look at both. Here is the first job. After some time, the second one started, and it's marked as a speculative copy. Well, we are not going to wait while either finishes. Let's move to the next topic. We'll talk about integral guarantees. This is a special type of guarantee, which is an alternative type to strong guarantee I mentioned above. While a strong guarantee says that, at each point in time, a pool may consume a certain amount of resources, such as RAM or CPU. An integral guarantee sees a pool as a repository, where one may accumulate resources. In these terms, say, the number of CUS is seen as CPU time, that is, CPU seconds. Thus, you configure a continuous resource stream that flows into the repository. Then, after starting an operation, you may consume all resources through the burst load. At the moment, you get a higher guarantee than you would in case you had a strong guarantee. Why would you need that? For example, you might want that when you do have a burst load, for example. When it comes to analytic operations you launch once a day. Such operations will quickly consume all available resources, and then the pool will be idle. In case of a strong guarantee, all guarantees would become useless. Well, they would be reallocated in a way, but money-wise, they are already paid for, while they are still idle. Conversely here. All right, let's create a pool first. I am creating the integral pool. I'll assign an integral guarantee to it, with a continuous stream of 1 CPU. As a preface, I will reconfigure the strong guarantees so that the alert we saw before does not appear. Now, let's create a pool and see how the guarantee will be piling up in this pool. Here we can see that every second, a new CPU second appears in the pool. Now let's run an operation in this pool. This operation wants to compose 2 jobs. Basically, the resources for one job will come from that continuous stream, while the resources from the other will be consumed from the accumulated values. Indeed, we can see that, with the time passing, this operation gets 1 CPU. Integral guarantee was the last feature I wanted to talk about. This concludes my presentation on the YTsaurus scheduler. For those who watched this video up to the end, I have a bonus. I said you can configure pools through the Cypress. Recently, we also added a feature to statically describe pool configuration through Terraform. Namely, we added a Terraform provider for YTsaurus, through which you can describe the static configuration for pools and more. Here is an example. We're creating a pool, tablet_cell_bundle, for dynamic tables, as well as some other Cypress objects. You can learn more about this example and see the guide for using our Terraform provider in our repository. I added the link to this repository to the video description. This finally concludes my presentation. Thanks for watching.